Okay, all right.
So Arif will be talking about supercomputing the universe, modeling structure, formation, and evolution. He is at the University of Victoria. He is a distinguished professor there, and he is visiting as the Infosys visiting professor over here. So, Arif.
Thank you very much. So you can hear me? Okay, good. I'd like to thank the organizers for inviting me. This has actually been a lot of fun. I've never seen so many young people attending an Astro conference, so this has actually been great in terms of having conversations. I've been invited here to speak about galaxy formation. Actually, my title starts out by saying modeling structure formation, and I will explain that really while my title says structure formation, I am really going to be speaking about galaxy formation, and I will explain very briefly the connection between them. The outline of my talk is described up there. So why galaxies? When I talk about structure formation, why galaxies? What makes galaxies special? Why is modeling galaxy formation hard? And we've made tremendous progress over the last 15, 20 years in terms of modeling galaxy formation. I will tell you a little bit about some of the successes. I will tell you some of the challenges. And if you're graduate students interested in working on galaxy formation, I will even open up a little bit of space at the end about potential directions where I see opportunities existing. So with that, let's start with the first slide. Galaxies sit at the confluence of two streams that have been animating this conference. There's cosmology on one side and large-scale structure, and then honest-to-God hard astrophysics at the other end. And what I mean by sitting at the confluence is that large-scale structure, as we understand it, is delineated by galaxies. It's the galaxies that trace out the filaments that stretch out across the universe. It's the galaxies that trace out the walls. It's the galaxies that define, to a large extent, groups of galaxies and clusters of galaxies. So galaxies really are the building blocks of cosmology, their large-scale structure. And so that makes them already a special objects to pay attention to. More importantly, galactic processes that happen inside galaxies actually have an impact on their larger environment. So they literally transform their environment around them, and in the process, that environment transforms the galaxies. So there is this nature versus nurture interaction going on involving galaxies. Galaxies sit right at the conjunction of all of that. Okay, I think this is, let's see if I can move it from here. Okay, so let's start with galaxies themselves. Galaxies form from initial density perturbations in the matter density distribution that we have more or less observed with the microwave background. And as galaxies evolve and grow, objects that we classically consider to be galaxies are really gaseous and stellar condensations. They are really structures that are made out of gas and stars, but they are inhabiting the minimum potential or the centers of a structure that extends much larger, about a factor of 10 larger in radius. And I'm, of course, speaking about the dark matter halos, which you can see up there in purple haze. And so when we think about galaxy formation, we cannot just focus entirely on baryonic physics. We need to be able to understand the interaction between the large-scale formation of the skeleton that's primarily driven by gravity and involves dark matter, and then there is the astrophysics and the baryons and the stellar physics that's playing out in the centers of these galaxies. So that then brings me to the next thing. When I say it's at the confluence, there is this whole spectrum of astrophysics that needs to be taken into account. I haven't actually done justice to it. I don't have enough space on the slide to cover all the areas that need to be covered. But just to give you a very quick idea, you have the interstellar medium inside the galaxies. You have star formation taking place. Stars will then eventually die or blow winds. The winds and the supernovae will give off energy and mass outflows that often combine together into coherent flows that will drive winds out of the galaxy. That affects the larger environment. You have stellar evolution that needs to be taken into account. You have metal enrichment from the stars that then changes the configuration inside the galaxies, because as the gas enriches, its cooling profile changes. So it's an ongoing dynamical system. You have gas and hydro dynamics playing out inside the galaxies, but you also have hydrodynamics playing out outside the galaxies. As the galaxy is falling in, for example, into a cluster of galaxies, you get ram pressure stripping. You have removal of gas. That leads to quenching of the galaxies. So all sorts of processes. Of course, we've heard about black holes here. We will be hearing another lecture later this morning about black holes and the role they play in terms of affecting galaxy and galaxy evolution. So you have a whole spectrum of physics that plays out in terms of affecting how galaxies are formed and how they evolve. And so in terms of understanding the cosmological simulations of galaxy formation, the objective is to simulate the evolution of a representative volume of the universe from roughly about 400,000 years after the Big Bang. That's where we see the fluctuation spectrum in the microwave background, to roughly today. And we want to capture all the relevant physics involved. What is the objective? What is the outcome? The outcome is we would like to have a realistic evolution of the universe. We want to be able to capture the emergence of galaxies. We want to be able to explain the properties of the galaxies, the full spectrum of properties that we see. We want to be able to capture the groups of galaxies and their properties, and clusters of galaxies and their properties. And of course, there's the whole issue of the reionization of the universe and the filaments, and you know, the list is in fact endless. But all of this starts with galaxy formation in the first instance. So if we are successful, we will be able to understand the physics shaping the observable universe. We will be able to interpret the observations. Because after all, observations give us 2 plus 1 or n minus 1 outcomes, in the sense that if you're looking in the sky, you're seeing positions of galaxies in 2 dimensions and you have velocity in the third. Or if you're looking at chemical compositions of galaxies, you have projection effects to worry about. Here we have full 6-dimensional phase space in terms of dynamics. In addition, we can actually trace the enrichment process itself. So once we have a system that is corresponding to the real universe, we can start to tease out the physics that is in fact evolving in a dynamical fashion. And of course then, if we get a handle on the physics that's shaping the large-scale structure and the galaxies, we can start to make predictions about future missions. What should we expect? We've heard, you know, I've had conversations with people here who have said, well, we hear that models are not working in terms of forming early galaxies that JWST is showing. Is that a real problem, or is that a problem with models, or is that a problem with our interpreting the models? Those kinds of subtleties need to be understood, and we do that by using these kinds of tools. And then, of course, if you understand astrophysics, then a lot of the cosmological probes looking at the large-scale structure, and I mean the cosmological structure of the universe, the evolution, the nature of dark energy and dark matter and their behavior over time, all of that becomes feasible from astrophysical probes, things like clusters of galaxies, but we need to understand the astrophysics that shape them before we can use them for precision cosmology. Okay, so why is it hard? It's hard because all of those processes that I have just described to you actually interact with each other. So, in fact, galaxy formation is driven by a complex networks, many networks of physical processes that often intersect with each other, and as they intersect with each other, they are influencing each other, and they're influencing each other in nonlinear fashion. And so the only real way to do this is numerically. So numerical simulations were, in fact, initiated in order to try and capture these complex processes, the interactions between them, and see if we can actually come up with a scheme that could capture all of these changing, moving pieces, if you will, simultaneously. It is hard because the problem is multi-component. It's a multi-scale problem in physics. The physical processes involved in shaping galaxy formation span greater than 15 orders of magnitude. We can only today, in the best simulations, capture 8 or 9 orders of magnitude. So there is a vast range of scales that remains to be understood. And in fact, of the scales that sit below this resolution limit, there are processes that we understand well, and we have to figure out how to encode them into the simulations, even though we cannot model them directly. And then there are processes we really genuinely do not understand. And AGN physics is amongst these. And so there is an uncertainty in the models at present that we are constantly trying to improve upon and, of course, push the frontiers ahead. And then there is the issue of how does physics acting at the subgrid level percolate and propagate up to the scale. A good example of that is turbulence. Turbulence cascade goes all the way down to molecular viscosity scales. We can't resolve molecular viscosity scales. And even normal simulations, you will find that the spectrum of turbulence is not Kolmogorov-Smirnov. There is a buildup of power close to where the resolution limit is. And if you can't get rid of that, you're already messing up your simulations. So we have to be able to understand how to deal with resolution effects. So all of these 3 points that I've highlighted here in combination make this an extremely challenging problem. I'm just going to give you a sort of a flavor of what I mean by hard. So dark matter, I would say, is easy. If you just had dark matter and you're only dealing with gravity, at least from a computational perspective, this is straightforward to simulate, and we can do a phenomenal job today. We can make really large simulations, we can do very high resolution, small simulations, and everything seems to work. But when you want to do galaxy formation, you have to have baryons. And as soon as you throw baryons into the mix, things get complicated in the way I've just described. And I'm just going to run you through very quickly through the list of things that we need to worry about when we think about galaxy formation. This is by no means a comprehensive list. It's just to give you a flavor of the kind of problems that we have to deal with. So there are direct processes that we can model directly. I mentioned that there are processes that work under the resolution limit of the simulation that we understand, so we can put in a known subgrid model to try and model its effects on the scale that we are simulating. And then there are processes that we really don't understand, and that's what this list here is. There we go. I guess I'm standing too far away from the transmitter. So we have gas. Gas is collisional, unlike dark matter. You have to deal with fluid dynamics. In fact, even the fact that we deal with fluid dynamics is problematic in some instances because the collision length scales are so long, they're getting out to about a kiloparsec or 10 kiloparsecs. And then you have to start wondering whether the fluid dynamics assumption itself is correct. But let's forget about that little problem for the minute. We have fluid mechanics, but we have to discretize fluid mechanics in order to do a simulation. Which method do you use? Which hydro method do you use? Do you use a grid method? Do you use a particle method? Do you follow an Eulerian scheme? Do you follow a Lagrangian scheme? Do you follow a mixed scheme? All of these makes a difference because every method has an advantage and a disadvantage. And so as people are making these choices, they are thinking through first which works better under the conditions and for the problems they're interested in. But then there's also issues to do with unforeseen consequences that you have to deal with. You have self-gravity. You have dark matter gravity that is driving the baryonic flow. You also have to worry about cosmic expansion. You have shocks, compressional heating, turbulence, thermal conduction, viscosity, etc. So all of these are tackled in the fluid equations through either direct calculations or through modified fluid equations in the case of cosmology, or through subgrid add-ons in the way I mentioned. Now gas cools. And as gas cools, it flows to the center of the potential well because pressure can no longer hold it up. When it's flowing in, it turns into a multi-phase flow. So now you have many components. You have cold clouds. You guys have all heard about high-velocity clouds sitting in the CGM, which are proving to be an extreme challenge for normal cosmological simulations right now because we cannot fragment the gas and form those kinds of structures easily. It's only now as we increase our resolution that we're starting to see those kinds of structures forming. So you have multi-phase gas, you have stars, you have black holes. Black holes and stars also have their own dynamics. They are collisionless in the first instance, but then there's also dynamical friction that you have to worry about, particularly in the case of supermassive black holes. Not all cosmological models actually do that. Some of the cosmological models just artificially take the black hole and pin it to the center of the potential. So when you're trying to do gravitational waves and merging kind of calculations, you have to be aware of what simulations you are using as a base in order to extract the information about merging black holes. Then you also have to worry about discreteness noise because a black hole of 10 to the 6 sitting in a dark matter simulation where the dark matter particles are about 10 to the 6 or 10 to the 5 are going to have two-body interactions which will artificially scatter the black holes. You have to worry about that. Are you doing a good job in capturing reality? We, of course, don't know how black holes form, how black holes grow. And of course, anything to do with black holes that has feedback related is at this point an open question. There's a lot of research going on people who are studying black holes. From a cosmological point of view, simulations point of view, we have two problems. Not only is the physics sort of ambiguous, but we also can't resolve those scales. So then we have to worry about making all sorts of ad hoc models, and then you have to ask, are your ad hoc models actually have any direct bearing to reality? And then finally, there are other physics that at this point are starting to be included in some limit. I just mentioned them here: magnetic fields, cosmic ray, and the inclusion of dust. This is showing you what the full spectrum of cosmological simulations look like. They fall into 4 categories. There is the zoom simulations. This is taking one object out of a large simulation box, refining it with incredible resolution, and then simply devoting all your computational power onto that object. And so you have a dark matter-only zoom simulations. You can have a large volume simulation of dark matter only, and these are the examples. There's the Millennium series of simulations, the Bolshoi simulations. Up here we have the Via Lactea, we have Aquarius and Phoenix, and then on this side, the added complication is that now there are baryons in the problem, and these are the zoom simulations, again, the counterparts of this, but with baryons in them. Examples are the Nihao simulations, the Eris simulations, some of the Fire simulations. They all have baryons. They're focusing on one object, and they are literally just basically beating down, and you see most of the simulations are essentially looking at galaxies like the Milky Way. Down here, you have the genuine cosmological hydrodynamic simulations. These are large-scale simulations. They range from 25 to 300 megaparsecs. They have gas in them. They have a resolution typically of about 1 kiloparsec, but you're forming a large volume, and you have a whole spectrum of galaxies forming in these kinds of environments. Now, subgrid models, because of presence of subgrid models in these simulations, we have to calibrate them. And so what is normally done is you take one or two known functions. In this instance, the one that's most popularly used is the galaxy stellar mass function at redshift 0. And so this is the points here are observations. The green line is showing you the calibration of SIMBA, one of the several simulation groups that are out there. And you can see, it matches well, but I just want to caution you, this match is determined, right? This is what calibration is all about. I have just opened up another one here. There is a whole slew of points back here now, blue and purple and red lines up here that correspond to the Eagle galaxy stellar mass function. The match between them is not surprising, right? This is calibration. They've all calibrated to this. So the fact that there is an agreement here is neither here nor there. Just one more that I have put on is the red line that has now appeared is the Eagle, it's the TNG red line. Again, the point being that there is all calibrated at this point. There is a oval there, which I just wanted to point out that because of the nature of the galaxy stellar mass function, the bulk of the stellar mass is sitting right there around the location of the Milky Way. And so a lot of these simulations being calibrated in this way are in fact being calibrated around the Milky Way mass and just slightly below the Milky Way mass. That's the mass range where the calibration is taking place. You need one other, at the very least, one other calibrator, and people choose a whole spectrum of calibrators. Some people, like TNG, have used the cosmic star formation history. They're looking at the star formation rate per megaparsec over a spectrum, over a range of redshifts. Eagle, for example, looks at the stellar density over a spread of redshifts. Romulus simulation is looking at the stellar mass, halo mass relationship, and the new SIMBA simulation that is being calibrated as we speak is looking at the black hole stellar mass relationship. So some people will use one or the other, and then they will predict or try and see if they get a match to the other distribution functions. So that's, again, something to be aware of. What are they calibrating to? Now, this is what you get out of it. I'm, of course, showing you the first example, the first slide I'm showing you is, of course, the best possible outcome. This is an outcome where stars, neutral hydrogen mass function, the black hole mass function, the dust mass function. This is the the SIMBA simulation, and you can see at redshift 0, it's capturing everything really well. So it was calibrated on the stars, but it's also getting the other modalities, the other observational aspects like hydrogen and black hole mass function and dust correctly. So this is what you get out of it. If you have a well-defined model, you start to recover the other features of the universe. And then, of course, the aim is that you hope that you get them all right, and you hope that you are getting the evolution right as well. The other thing that you can do is you can start to look at the morphology of the galaxies, and now we're reaching a point where the resolution of the simulations are getting high enough that you can start to do that. And you can see that the spectrum of morphology here is successfully replicating the galactic structure and diversity. You can also look at the, You can also look at the galaxy stellar mass function going back in time. So this is the Simba on your left. You can see the Simba mass function. I showed you what it was like at redshift 0. At low redshift, it's matching the data. And then you can compute it backwards in time. In this case, the plot goes back to about redshift of 6. And you can see that the match is actually quite good, all the way back to redshift of 6, given the fact that the data is quite sparse at redshift of 6. This on the right is the Eagle galaxy stellar mass function. The match at low redshift is not surprising, but as you go back in time, you can see that here the match remains good until about redshift of 3, and then at redshift of 6, you start to underpredict galaxies. So these are the kinds of things that you would look at when you are trying to use these simulations for predictions. What do these simulations do and what they don't? So these are just pointing out what I just said. And you can also look at other mass functions going back in time. Now, I want to highlight that calibrating to the same function like the galaxy stellar mass function earlier does not guarantee that you get everything in agreement, as I pointed out with the galaxy stellar mass function. So here you have the H1 mass function at redshift 0. You remember that I had said that the Simba was getting the mass function right, and it is here. TNG is doing pretty good. Eagle is actually falling under. That's at redshift of 0. And then you can look at that as a function of redshift to see what happens, and you can see a divergence in evolution behavior, even amongst these three simulations that are right at the top of the field right now. So let me recap. You have galaxy formation models. We've made considerable progress. I've written 10 years, but really over the 25 years. It started 25 years ago. This program, and we've made tremendous progress over the 25 years. The models can successfully capture and replicate Milky Way-like galaxies and sub-Milky Way-like galaxies. They can do more or less, depending on which model you're looking at. You can look at the observables going all the way back to redshift of 6. But the problem is, since you've calibrated it at around the Milky Way mass, you want to stress test it, and one way to stress test this is to ask what happens when you look at more massive galaxies. So the first thing you can look, when you look at the very high resolution simulations, you can ask what the morphology of these galaxies are, and you find that you get your standard expected early type galaxies, but you also get groups whose central galaxies are late type galaxies, disk galaxies, forming stars. Now, this turned out to be a surprise. It's a surprise because most of us think of central galaxies in groups and clusters to be red and dead galaxies, but they're not. And in fact, the fact that we don't know about this is more to do with bias in the observations. The observational samples of groups are chosen in such a way that they focus on a specific class of objects. If you go and read the observational papers, for example, of Sauron or Clog's sample, in there's a throwaway line that says we focused on galaxies, on groups with early type central galaxies. So by definition, they've filtered out the objects that belong to this class. There is now a more statistically complete, a representative compilation underway going on in Finland, and so we will hopefully have a better measure. But from case studies done with MUSE, we already know that there are galaxies that are early type. So I'm going to. The other thing I wanted to talk about is the fraction of galaxies that are star-forming versus not star-forming, particularly at the high mass end. And here I want to just point out that observations show that 70% of the galaxies, like the brightest central galaxies in groups and clusters, are quenched, but 20 to 30%, 25 to 30% are forming stars. These are the galaxies that are sitting up there. Now, if you go and calculate these in all of these simulations, you will find a completely incorrect fraction. So if you look at Romulus, in Romulus you find something like 40% is quenched, and if you go to the next mass up, only 15% is quenched, which means 85% of the galaxies are happily forming stars. They shouldn't be. Then you go to the other simulations, Simba, Illustrious, Eagle, and you look at their fraction, and you find that the quenched fraction is 100% or 90%. And so basically they do not have any galaxies that form stars. And that too is a problem. So all simulations have a problem. So this is one of those issues that I wanted to highlight. And I have 1 second. I will maybe skip over this slide. It's the second last slide. It's just saying that we cannot form groups and clusters of galaxies properly. We just cannot do it. We do not get the observable properties of galaxies, groups and galaxy clusters correct. So this is a generic problem with all the simulations today. And so that's where things stand. Rather than read this, you've heard me go through all of this. Basically, you know what the requirements are. We're pushing ahead with stress testing. People are starting to challenge these models. And what we find is that there are failures. And you won't hear about this at conferences generally, because if I was I am a Simba proponent and a Romulus proponent, but if I was genuinely a Simba proponent, I wouldn't open up the hood of the car and tell you what's inside. It's like looking at a shiny new car and seeing oil drips inside. I'm here telling you because as graduate students, you should be aware of the oil drips, because that's where the opportunity lies. How do you fix these models? I'm just going to point out to you two things. One is AGN feedback. We do not do it correctly. We know this, that our models are ad hoc, and doing a much more realistic treatment of AGN physics in cosmological simulations really is the next frontier. And then the other one is there are several people in the audience who are already starting to work on this. I mentioned that we have this gas, the gas fragments turns into multi-phase structure, but we do not capture that multi-phase structure correctly in these large simulations. And that too is an area that's important, because this gas eventually will fall in and trigger star formation or trigger AGN feedback. It's a coupled system. We cannot have one piece that's not working right and hope that we get the whole thing correct. So I will stop here. I have a movie that I'm going to let play as I take questions. This is an illustrious simulation. It's eye candy to impress you as to what has been done. And of course, they have tons of money, so they've made a beautiful movie. And I will stop.
Thank you, Arif. We have time for questions.
Hello, thank you for the talk. I had a doubt regarding the BCG being not just early types, and there are other types of galaxies as well, which is not openly told. The paper mentions only it considers only the early types. So I just wanted to know how the even late type galaxies can survive in such a dense environment in the middle of clusters.
How they can survive as disk galaxies in these environments?
Yes, like how maintain structure and shape, like maintain their morphology.
Sure. So one of the slides I skipped over showed, so there was a very old paper, old meaning early Sloan paper, that looked at the morphologies of central galaxies in groups identified through optical measures in the Sloan survey. And they also find the same thing, that at the low mass end, you have the central galaxies are early type or preferentially early type at 60%. And then as you go up in the mass scale, they drop down and drop below 40%. And the argument of survival is, think about a Milky Way. You're starting with the Milky Way. Let's imagine that it accretes matter not through a merger with Andromeda galaxy, but it accretes matter through smaller mergers, which really do not disturb the central galaxy very much, but grow the system. So as groups grow, they will preserve the morphology of the original central galaxy that they have. But eventually, as they grow bigger and bigger, they encounter bigger mergers. And those bigger mergers do destroy the central galaxy. They transform them from from spirals to elliptical galaxies. And we see this trend. We see that as systems get bigger and bigger, more and more mergers have been experienced. There is a transition in morphology. But that's not the entire picture. Gas also cools down in these systems. So even though, we have in the paper, with one of the papers I referenced up there is Young et al., 2021. There is a sequence of evolutionary images shown where you have a central galaxy that's late type, undergoes a merger with nearly equal mass galaxy, will transform into an elliptical galaxy, and then short while later, short meaning several giga years later, the gas around it starts to cool, and you start to form a disk. So we call this the rejuvenation of galaxies. And I think a lot of the objects that we have seen in the MUSE case studies are in fact rejuvenations, because the disks are gaseous. They haven't really started to form stars in a significant fashion. There's only one or two examples that I know of where there's actually active star formation going on in the disks. So, it's a dynamic process. They get destroyed, you're absolutely right. There is a drive towards destruction, but you can't forget the rejuvenation channel.
Thank you.
Yeah, thank you for the talk. So I was wondering about this, all the cosmological simulations.
Sorry.
Yeah, all the cosmological simulations are producing the bar fraction, the morphology of the galaxies with a less what we see in observations at current redshift. So, and there are many other tensions with lambda CDM, like pattern speeds of bars are higher. So, where is the direction to resolve these issues? So according to your point of view, I wanted to ask.
Yeah, so I think that trying to understand bars and pattern speeds of bars and the internal dynamics of galaxies, you really have to go to these zoom simulations. The simulations like Nihao or Eris. TNG, Romulus will not give that to you easily because the resolution isn't there. And so, you may get results that are interesting, and you may get results that, sort of go in the direction of observations, but if you really, really want to do justice to the internal dynamics of galaxies, you need to go to the simulations where you're actually drilling into the galaxies. Now, having said that, do you get an exact match with all of these simulations? The answer is not entirely, partly because when you're dealing with the central galaxy and you're looking at bar formation, how strong the potential is in the center plays a role. It can either suppress the bar. For example, if you have a very strongly cuspy central environment, you will suppress the bar for a while. So a massive black hole starts to play a role. If the massive black hole is wandering around, that can have an effect on your bars and your bulges and central stellar halos. And you can even go so far as to form stellar cores. You can get, what's the word I'm trying to remember? Scouring. You can get black hole scouring happening in the centers where you get these effects going. But all of this requires very high resolution. I think there was a run right now, Giga Eris. There's one paper on Giga Eris out. It has a resolution of 1,000 solar masses. It's a Milky Way-like galaxy. There's only one galaxy that was done. It was pushed down to redshift of 4 and it stopped. Cannot run it any further down. So that's a computational challenge that we also face.
Okay, thank you.
Since you're not worried about looking under the hood, so I just wanted to ask about the Simba calibration. So if you look at the stellar mass function, there is an offset in the observations compared to the predictions from Simba, even at redshift 0. I think you pointed to it in your slides, but then you did not talk about it. Do you want to comment on it?
I will, if I can, let's see if I can quickly go back.
Yeah, just a little bit. Okay, fine.
You're talking about this slide.
Yeah, yeah.
Yeah, so the blue here, which is Simba, is the older, slightly older Simba. The green here is the new Simba calibration. So what you've pointed out is absolutely spot on. There are glitches here and there. In this particular instance, the only thing that was changed is the chemical evolution of the model. So earlier Simba was doing a global enrichment of the disk. Now the new revised model has localized enrichment, and the cooling that changes that makes a difference on the galactic scale. So you see how sensitive these things are.
Yeah,
and so getting the right physics in makes all the difference.
No, but the question is also whether there are degeneracies, right? Because there could be
Yes.
multiple things which could fix the same thing.
That's right.
And then the question is, how do you go about testing?
Yes, absolutely. So people who work on galaxy scale problems, or people who work on global properties of galaxy groups, like the X-ray luminosity versus X-ray temperature and whatnot, have played this game. They tweak AGN feedback. And then they say, well, we don't know what AGN feedback does, so we have the freedom to tweak it. And that's one of the ways you play with the degeneracy to your advantage. But what I didn't get around saying in my last slide was, no matter how you play with your AGN feedback, and no matter how good you get the global relationships right, the individual profiles are wrong. And so it's the observers. This is a point I would really like to make here, and I might as well take this opportunity to do that. If you're an observer, do not use these simulations to prove, to say, oh, look, we are getting a good result. Your job as an observer is to poke holes in the theory. This is how I was brought up. As a theorist, my job was to come up with a story. And the way my supervisor taught me is that every good theorist should be able to come up with 4 different stories for every observation. It's your job as observers to go and poke holes in them and tell us which one is right. Do not drink the Kool-Aid of the simulators. All right? And I'm a simulator, I'm telling you this. But I think that if you push us, we improve. If you join our bandwagon, we just don't have an opportunity anymore to move forward. And this is a culture shift. I've noticed this culture shift. Avoid this culture shift. I've seen some very, very, very smart people in this audience. You have the opportunity to push the field.
So, thank you, Arif. It was a very interesting
Gauri, I
talk.
think we will stop here.
Okay.
You can carry on discussion offline. We are
Okay,
already
no
done.
worries.
Yeah, I'm happy to talk at T-Time.
Thank you, Arif. Thank you so much for the talk. We'll switch the order of the remaining 2 talks for technical issues. So request Professor Preeti.
You need to turn this off first.
Excuse me, madam.
So there is one quick announcement. There is a YOLO case with spectacle insights which is lost. If you found it, please.
It's okay? Yeah.
There is a YOLO spectacle case with spectacle inside it which is lost. Some participant. If you have found it, please bring it to our notice. On the other hand, last night we got one spec which, if any of you have lost your spec, please come back to us. During the dinner time, we got it in the dining area.
Okay. It has a pointer as well?
This is pointer.
Okay, okay. It's okay. I think I'll probably use this directly. It's fine. Okay. Just should I begin?
So it's 30 plus 10?
Okay,
Your
sure.
5-minute working hour.
Okay, sure.
All right, so Professor Preeti Kharp will talk about radio-quiet AGN and their impact on galaxies. Preeti, all yours.
Thank you, Jasjeet. So I'll start by thanking the SOC for inviting me to give this talk, and I want to also thank Arif for an excellent introduction about the complexity that is galaxies and AGN. And I'm going to talk about a certain class of AGN, and I think you will realize very soon that this is also a very complex type. So this is the radio-quiet AGN, and the question is whether they have impact on their host galaxies and how. So I'll start by just a very brief historical background. It was in 1943 that Carl Seifert recognized a class of spiral galaxies which were peculiar, in that unlike normal spiral galaxies where you have an increase in the stellar density towards the centers, as you can see here, there was a small fraction of galaxies which seemed to be superimposed by a star-like nucleus, which you can see here. The nucleus was so bright that it could outshine the light of the entire galaxy, and sometimes even 1,000 times more than the light of the entire galaxy, which is made of 100 billion stars. The second thing that he noticed was the spectra. The spectra of a normal galaxy is of this sort, which is dominated by absorption lines, and this comes from the photospheres of the stars which make this galaxy. Whereas on the other hand, you had a spectrum of what we now call an active galactic nucleus, which was dominated by emission lines, very broad. So this is a broad line, which is, there is a narrow line on top of it. These are narrow lines. Very prominent emission lines were observed in the spectra. So these were the two signatures of what initially were called active galactic nuclei, a star-like nucleus and emission lines. It was another 20 years before radio interferometric imaging became routine, and then that is when this work really started, was the discovery of radio jets in these active galaxies. So on this side you see this is a superimposition of two colors. So the blue is the optical light, where you see the host galaxy, which is an elliptical. And the red emission that you see is radio waves, which are emitted in this case in bipolar outflows, which can extend way beyond the host galaxies themselves. This is the host galaxy. And this is just a high resolution image of the same AGN. So these are now what we call radio loud AGN. Most of the AGN were actually not as spectacular. They were like this. Where you see now the green light is from stars in the spiral galaxy. You can see the spiral arms, etc. The red color that you see here is hot X-ray emitting gas, and the blue-pink emission here is the radio emission from this galaxy. So these are radio-quiet AGN, and these happen to be the majority of active galactic nuclei. So this, because I'm going to say I'm talking about radio-quiet AGN, I do want to flash this slide, which is where it kind of started, was the work by Kellerman and group, where they basically were looking at the Palomar Bright Quasar survey and looking at the radio and optical properties of these. And what they found was that when you took the ratio of the radio flux density of these active galaxies with respect to their optical emission, there seemed to be a clear bimodality, as you can see here. So this is the R parameter for the entire sample. And there you see that there's a very large peak here, which has R values less than 10, and a smaller peak here with R values greater than 10. So this is the radio loud, radio quiet divide. And it's a very important open question in AGN physics is what makes AGN radio loud versus radio quiet. So before we talk about some of the explanations put forth to explain this dichotomy, I do want to show the basic ingredients of an AGN as we understand it now. And this is on the basis of multi-wavelength continuum observations as well as spectroscopic observations that this kind of a model of an AGN has come about. So this at the center, we believe there is a now we know there is a supermassive black hole which has 1 million to 1 billion solar masses. Matter accretes onto the supermassive black hole through an accretion disk. Then there are very dense, fast-moving clouds around this black hole accretion disk system, which are the ones which give rise to these emission lines that we saw, that Carl Seifert saw in their spectra. And these, the ones which are, the fast-moving clouds are the ones which give rise to these broad bases or wide lines that you see in the spectra. Further away, there are other clouds which are not as dense and they're moving slower. And so these are the ones which give rise to the narrow emission lines that you see in the spectra. And so on the basis of these different types of lines that you see, AGN have been subdivided into different categories, primarily type 1 and type 2. Type 1s are the ones where you see broad lines and narrow lines, and type 2 are the ones where you see only narrow lines. And that is explained by the fact that there is some obscuration happening probably in a torus-like structure, which is hiding the broadline region and the accretion disk system from certain lines of sight, so that when you don't see the broadline region, you only see narrow lines and you see a type 2 object. Now, each of these ingredients of an AGN are separate subfields of study. People study different parts of this AGN, and for example, you all know that the discovery of the supermassive black hole in the Milky Way got the Nobel Prize in Physics in 2020 by Gez and Genzel. And the second thing I want to point out is we have this cartoon here is, the reason is that we can't actually image this. We don't have, as yet, telescopes which can actually have the resolution to grow all the way down, except at radio frequencies. And that is why we have now, because of the Event Horizon Telescope, the actual shadow of the black hole in one of the active galactic nucleus. So coming to the second important question, how do these, or rather AGN feedback. So AGN feedback was arrived at from several different observational evidences, and I'm just presenting two of them. There are many more. So one was this very close correlation that was observed between the black hole masses and the luminosities of the bulge, galaxy bulge. And there was an even tighter correlation between the black hole mass and the stellar velocity dispersion in the effective radius. So somehow the tiny black hole seems to influence its host galaxy. So that is where AGN feedback was suggested. The other thing was when X-ray telescopes, including ROSAT and Chandra, looked at the centers of galaxy clusters, they found a lot of X-ray emitting gas, but also the presence of X-ray cavities, which you can see here. So this is a deficiency of X-ray gas in the centers of clusters. And it was soon found that these cavities seem to be filled nicely with emission from AGN, the radio emission from jets and lobes of AGN, as you can see here in this image. So the red contours is radio emission in the center of the Perseus cluster of galaxies. There's also the cooling flow problem. There is also the galaxy luminosity function relations, which are suggesting that there is AGN feedback. But how does it happen? It's not very clear, and especially in the case of radio quiet AGN, which are actually the majority of AGN. So how does it actually happen? So today in my talk, I'm going to talk about a particular two types. So radio quiet AGN consist of both Seifert galaxies, which I already mentioned, but also liners, which came about much later in the 1980s. So these liners is basically an acronym for low ionization nuclear emission line region galaxies. And their spectra are very similar to the Seifert type 1s, so rather type 2 narrow lines, but they also have the low ionization lines are much more prominent than compared to the Seifert type 2s. There's also radio quiet quasars, which belong to the radio quiet AGN class. But I'm focusing today on Seiferts and liners, which are the low luminosity end of the radio quiet AGN population. So these have low Eddington ratios, which is basically a ratio of the bolometric luminosity to the Eddington luminosity. And the bolometric luminosity basically comes from taking the O3 emission line luminosity as a proxy, and Eddington luminosity is a function of the black hole mass. So these are very small values for these very radioquiet low luminosity AGN. And because of these low Eddington ratios, the accretion disks are expected to be different. So they're not the standard geometrically thin, optically thick disks, but rather radiatively inefficient accretion flows, which are more puffed up. And as I already showed in the previous slide, the radio emission in these radioquiet AGN is on much smaller scales than what you see in radio loud AGN. The emission can be just a few hundreds of parsec or a few kiloparsec in extent. Now, on the right, this image I already showed you previously, and now I'm showing the same source with radio contours. And as you can see immediately here, the complexity of the source. So even in this, the work, this is from the paper of Gallimore et al., and they also describe the structure as a vaguely linear but highly structured source. So it's not a very clear jet-like, lobe-like structure that you see in radio loud AGN. It's much more complex. It's not, for example, clear where the core of the radio core of the source is. Core is the unresolved part of the jet in AGN. So it's much more complicated when you come to radioquiet AGN. The other thing, for the longest time, there was the suggestion that this radio outflow is not just from the AGN, but maybe from some starburst super winds which are coming from the nuclear regions. So there has been a lot of debate whether the radio emission that you see in radioquiet AGN is actually even from the AGN. So one way to confirm, to check if it's true that the radio AGN is supplying the particles and fields to the radio lobes is to actually carry out a very long baseline interferometric study. So this is just an introduction for VLBI. VLBI is when you can take radio telescopes which are not physically connected, unlike the interferometers like the GMRT or the VLA, when you can take telescopes far away from each other and make them work like a single telescope. And because you can have arbitrarily large distances between these telescopes, you can have arbitrarily large baselines or resolution. So the resolution is lambda by d. D is the diameter of this telescope, and in this case, it turns out to be the largest separation between the radio telescopes which are working as a single telescope. So because you can make these arbitrarily large, you can even have telescopes in space and on ground work together. You can increase your resolution by a large factor. So typically the VLBI arrays that operate on Earth, like the VLBA, very long baseline array, which are 10 antennas spread across the US subcontinent, they work together and give resolutions of a milli-arcsecond. So compare this with optical telescopes, ground-based telescopes, which are arcsecond resolution. So you already get milli-arcsecond resolution with this. And if you then also take care about the lambda in the resolution formula, you can go to higher frequency waves. So millimeter wave VLBI is what you get when the Event Horizon Telescope is a millimeter VLBI array. And you know now that it can do wonders and actually get the actual shadows of black holes. So here, the only thing I think I missed mentioning is that to carry out VLBI, you basically need very highly accurate clocks, and that timestamp data is what you need to finally correlate the data later. So I'm going to talk about a study of a very small sample of radioquiet AGN. This is, this is a sample which belongs to the KISAR survey. And KISAR stands for Kitt Peak National Observatory Internal Spectroscopic Survey, RED, of emission line galaxies. And what we started doing with this sample was, they were sources which were exhibiting double-peaked emission lines in their spectra. So this is what you see in the spectra. And these double-peaked emission line AGN are very interesting because people have suggested that they could be black hole binary candidates, in that each of the black holes then has a narrow line region associated with it. So then you have two black holes in two narrow line regions and you have these double-peaked lines. But also there are other explanations for double-peaked emissions. They could just be the jet itself is pushing the narrow line clouds in two opposite directions, then creating this split in the peak. So we carried out a VLBI survey of this small sample of Kissar sources, and our selection criteria was the presence of double peak lines, and the second criteria was that they should have been already detected by some radio survey before we could do VLBI. So they were detected with the Very Large Array first survey, which has a resolution of 5 arcsecond at 1.4 gigahertz, which is the observing frequency of VLA first. So let me just tell you now the interesting results that came out of this study and how they kind of eliminate the question of radio quiet AGN. So what we found was that even though, if you see on the top here, this is a radio optical overlay. So this is the color image is the host galaxy. It's a spiral galaxy. You can see the spiral arms as well. The green contours is the radio emission from this spiral galaxy, this AGN. And following the definition of radio quiet AGN, the radio emission is very compact. You don't see any jets. You don't see lobes that you saw in those beautiful sources like Perseus A. It's just a point source, very weak point source of just a few millijanskis. But when you start looking at them with VLBI, you start seeing that they have jets. And so this is one of those, this is the same source, Kissar 434. And you see 150 milliarcsecond long, 150 parsec long VLBI jet at 1.5 gigahertz. And what the other thing to note is that this seems to be a one-sided jet. So you don't, so this is the base of the jet, the core, so-called core, and core jet structure that you can see here. We don't have emission on the counter jet side. So normally when you see a one-sided jet in radio loud agent, it's a signature of Doppler boosting effects. So because the plasma in these jets has a bulk relativistic motion, so that emission, the jet which is approaching you is brighter in the observer's frame and not in the jet frame. And the jet which is moving away from you is the emission is actually Doppler dimmed, so you don't see counter jet emission. So when you see one-sided jets, it's usually a signature of fast jets. And that's what it seemed to be in this case. So we tried to kind of get estimates of limits on what speeds may be implied by the presence of this jet. We tried to estimate some kind of a jet to counterjet, surface brightness ratio. In this case, there is no counterjet, so that will be just the noise in the counterjet direction. And so we use those limits to derive some limits on speed. But to do that, you also need to have some idea about the inclination of this jet. So if you remember your relations from special theory of relativity, you need to know both the speed and the angle to kind of make sense of this situation. So we don't have angles. But we know that these are type 2 AGN. So type 2 AGNs are the ones where you see only the narrow lines. And so we think that they must be oriented, or rather they are oriented in the sky in such a way that we are missing their broadline region. And so they must, because the torus, which I showed you in the first few slides, has an opening angle of around 50 degrees. We think that these must be oriented at some angles greater than 50 degrees. So we have some limit on the angle from that. And using that limit, we tried to get a speed limit, and that turned out to be large. So velocity was around 0.75 c. We found this to be the case with all these very small sample, but all the sources, almost all the sources seem to have jets, and they seem to have fast speeds limits that we derived. So this sample turned out to actually have more than 60% in the first epoch had jets, and in the second epoch it turned out that 100% of them had jets. In the sense, the second time when we re-observed them, we found that there was jet emission that we didn't see in the previous epoch. So this number is much larger than what is actually observed in larger samples of radio quiet AGN. And we believe that is the selection criteria that is kind of biasing our results. And I'll tell you why that's interesting. So we derived some range of jet speeds, which are not completely, they are on the higher end are actually higher than what are seen in typical radio quiet AGN, but there is an overlap in the speeds we derived, the limits we derived, and compared to the actual speeds people derived by multi-epoch observations. So it was interesting to consider the question that maybe Doppler boosting effects are actually happening in radio quiet AGN, which means that these jets are also fast. And so just recently, we found that in one of those 8 sources, when we carried out the second epoch observations, we found that the jets are actually moving superluminally. So this is now an actual, we had limits earlier just on the basis of the jet to counterjet. We now have actual estimates from motion of these jet components. And so this is in the liner galaxy called Kissar 872, where this jet knot seems to be moving at a speed of 1.65 times the speed of light. So again, superluminal motion is something that's like an optical illusion. It's because the jets are moving very fast and they're probably aligned at small angles to line of sight that you see this effect. It looks like things are moving faster than the speed of light, which of course is not physical. But what this tells you is that the jets are indeed fast in radio quiet, some of these radio quiet AGN. And just 2 months ago, we found that another candidate from another source from this sample, Kissar 102, which we initially thought was like the best binary black hole candidate we could find. So in the first epoch, we just saw this emission, which seemed to be like two compact components, and A and B I call here. And this is the same thing with spectral index superimposed. We could detect at one frequency, we detected both the components, and the second frequency, we detected only one of them. So we could get just a spectral index for one of them, and that was inverted. And an inverted spectrum is a sure sign of a self-absorbed base of a relativistic jet. So, but because the second component was not detected, we thought that would be inconsistent with the core jet structure, and this could be a binary black hole. But when we carried out the second epoch observations, we found that the second component is indeed moving, and it is also superluminal. So this is turning out to be 1.4 times the speed of light. So overall, these second epoch observations are suggesting that these very low luminosity radio quiet agents seem to also, first of all, have jets and fast jets. So that was a revelation. The other thing we found interesting was that when we looked at their SDSS spectra and along with the radio data, so this is now a plot showing line ratios, which is O3 by H beta and N2 by H alpha. And these grids that you see are for different models to explain these line ratios in AGN. So for this, we use this plasma modeling code called mappings. And we tried several different models to see what explains the observed line ratios in these sources. So the models are very degenerate, and photoionization seems to actually explain all the line ratios. But for sources which have jets, we also found that this model called shock plus precursor seemed to explain a lot of these data. So what this is suggesting is that the jets are not in these radio quiet AGN. Of course, this is very small sample results, so we should keep that in mind. But it seems like the jets are not directly shocking the gas, but somehow the post-shock gas could be photoionizing the gas around it. So somehow jets are playing a role in influencing the host galaxy environments. The second, another piece of evidence was that these line peak separations were of the order of a few hundred kilometers per second, the double peaks. But this is much smaller than what you expect the jet speeds to be. So somehow the jets are influencing the emission line clouds, but not by pushing gas maybe in front of them. But maybe they are moving gas in a lateral direction. So that was our conclusion. So either the emission line gas is being pushed in a lateral direction by the jet, or the emission line gas itself is arising in a wider outflow around the jet. So this is what is shown here, like the jet maybe, and there's a wider wind around it. So this kind of a stratified outflow has also been suggested from many different angles. So polarization work that Shilpa Shashikumar had spoken about in her talk, that was suggesting stratification as well based on polarimetry. So all these results are suggesting that the radio outflows in radio quiet AGN are not simple. There may be multiple components here. And now we come back to the same question. When we said that we see many more jets in our sources and we think it's a selection bias, it looks like the jet NLR interaction is the reason for the double peak line splitting. And so we seem to have picked a sample which already was dominated by this jet NLR interaction. So this is also a signature of jet mode AGN feedback in radio quiet AGN. So I'll now start to wind up my talk by giving two examples where this is kind of the next step that we want to take, is to first carry out a multi-scale study. So multiscale is, I mentioned in the previous slide, I mentioned these nested outflows, like outflow and faster outflow in the middle and then a slower outflow at the, on the outside. This is a case of a nested outflow where all the different outflow components are in different directions. So now this is the Cepheid galaxy called NGC 2639. And all these images are of the same galaxy at different resolutions at radio frequencies. So this image is actually a GMRT image, which shows these lobes. The extent of these lobes is just a few kiloparsec. But a higher resolution VLA image shows that the center of this source has another radio jet in a completely different direction. The even higher resolution VLA image of this source shows another radio outflow in a different direction. This is 360 parsec. And then the VLBI image shows a 3 parsec scale jet in a slightly different direction. So looks like the radio quiet agent are much more complex. They have nested outflows, but they also may have nested outflows in different directions. In this source, we also found that when you look at the molecular gas, so here now, this is the largest structure and the molecular gas image that we got from the Karma Edge survey, which shows clearly that there is a deficiency of cold molecular gas in the center where the jet is. And so this is the just the total intensity image, and this is the velocity dispersion image, which seems to also show that there is some kind of increased dispersion at the edges of this radio outflow. In the bottom two panels are the Galax near UV and far UV images, which are telling you about the star formation. And so there seems to be also a deficiency of star formation in the region where the CO gas is missing. So it looks like there's some star formation quenching which is going on. We could also derive, because we have multi-frequency observations, we could also derive spectral ages of each of these different episodes, and they turned out to be of these orders. And so it looked like every 10 million years there was a different outflow which was kind of was beginning. So it looks like agent feedback. So agent feedback, it looks like a good signature of an agent feedback, and the agent feedback itself could be enhanced by the fact that this is episodic and in different directions, but it could also lead to episodic activity in the sense that you are throwing material away and then matter then finally falls back and accretes and there is a new outflow. So it's all much more a cyclical complex process. The final image I want to show here is now the next step, which is actually what we want to do finally is not just look at the radio emission, but actually look at multi-phase gas emission. And this is one of those multi-phase gas studies. This is work by Aishwarya Girdhar. So this is another radio quiet agent. It's a very small jet, 1 kiloparsec long, and this contours are the radio jet. The colors, pixels that you see here come from ionized gas. This is ionized gas, O3. And this is molecular gas, CO. So here, what they find is that there is an increased ionized gas at the edges of these jets, but not so in the molecular gas, only in the ionized gas. There seems to be even a depletion of molecular gas at the edges of the jets. But there is an increased dispersion transverse to the outflow. So here, these are the velocity velocities given here. So the purple is the higher velocity dispersion, and that happens to be lateral to the jet. So this kind of it seems to be a case of positive and negative feedback going on in the same small environments of this central of this radio quiet AGN. So this simultaneous positive negative feedback, they've also been, of course, they have been observed in hydrodynamic simulations also, which suggest jet ISM interactions in radio quiet AGN. So this is work led by Dipanjan Mukherjee and students. So overall, it looks like the jets in radio quiet AGN, okay, first of all, there are jets. And they seem to be capable of influencing. So I've just used influencing because we don't know the details of how the process works, but they seem to influence their local gaseous environments. And the impact is probably greater because these outflows themselves are stratified, so they basically have a larger working area, right, to influence the ISM. They are stratified. They also, outflows are also probably multi-phase. So we are seeing only the synchrotron plasma, but there is also ionized gas and molecular gas, which is being, which is also outflowing and being impacted. And plus that they are episodic. So they're short-lived and they have multiple episodes which produce these outflows. In turn, because of all this complex phenomena, the jets themselves could be slowing down and dissipating, and that could be the reason why we have radio quiet AGN to begin with. I mean, you don't have large jets because there is all this interaction which kind of stifles the jets and make them radio quiet. So this is my overall summary. Majority of AGN are radio quiet, and there is still a lot of debate whether actual collimated jets exist in radio quiet AGN, similar to radio loud AGN. And it's not clear if and how they actually impact their surroundings. This kind of so we have shown in our study that VLBI is the way to go to probe radio emission on smaller scales, and regular VLBI monitoring is the need to carry out to understand what is happening in these AGN. This has not been carried out, and that's the obvious reason is because these are radio quiet, they're radio faint, and VLBI, it becomes much more difficult to carry VLBI, and you need much more sensitive VLBI to actually be around before you can do this kind of a work. We found that the Seyfert and Liner galaxies that were chosen on the basis of double peaked emission lines show a high fraction of jets, and I think this is a selection bias, which says that these, it's because the jet NLR interaction is the reason why you're getting double peak lines. Jets in AGN, radio quiet AGN, influence their environments, which makes them agents of jet mode AGN feedback, and jet feedback could slow down jets, cause episodic jet activity, which will then cause even greater feedback and the making of a radio quiet AGN. So I'll stop here. Thank you.
Thank you, Preeti. We have time for questions. Suchetna?
Thank you so much. Very great talk, Preeti. Just two quick questions. One is, from your study, where does the status of this radio dichotomy stand now? I mean, I think you sort of addressed that. And the second is, you did mention hydrodynamic simulations. So I was thinking that, you also have wind mode of feedback from, let's say, wind feedback, like radiative feedback.
Yes.
So do they have any connections in, there's an interaction of the wind feedback with the jet feedback. So how does that come into your study?
Okay, so the question of the radio loud, radio quiet, I think that's an excellent question. We are finding some of these very weak radio sources also tend sometimes to have R greater than 10. So it's this R value of 10 is like, we always knew it was arbitrary, but I think as you look at more and more sources, we feel the need of giving up on this R value. So I think it's it seems like a much more continuous property change between radio quiet, radio loud. So maybe it's not drastically different phenomena. I think that is the impression we get from all our work, that it's radio quiet AGN are probably not drastically different from radio loud AGN. But there are obviously many more things happening because of these interactions. The question about the jets versus winds. So I think the simulations, so the simulations I think don't really have very collimated jets, but now the question of jets, like what makes a jet? I mean, so when do you call an outflow a jet? So I think most of these simulations, I think they don't really differentiate between a very collimated one versus, but what they mean is maybe gas outflows versus synchrotron plasma, right? I think that ISO, yeah. Right. So for our work, we have so far been, we've confined it to radio data, so that makes our work a little bit limited. I mean, we are probing just the synchrotron plasma, but I think that's the next thing we want to do is also look at emission line gas. Yeah.
So hi Preeti, I was curious about those multi-scale jets that you showed.
Yes.
So these multi-scale jets, what is the reason that you see them at different directions in different? That's the first question, because I saw you go from 9 kiloparsec to 3 parsec, the example that you showed.
Yes.
And secondly, is there some way, because there are jets associated, you will have a disk also.
Yes.
So is there a possibility that one can detect a disk, or by any chance we are seeing an ionized disk? I'm just wondering about that.
Right, yeah. So that's an excellent question. So this 2639 is not even the first source which shows these kind of multiple things. So this was the hand-wavy answer we gave also for the first time we saw this, was that maybe there are minor mergers that happen on much smaller scales, like a few million years, every few million years. A minor merger could even be just a molecular cloud, falling into, the black hole. And every time a merger happens, you have the creation of a new accretion disk. And that direction of the accretion disk then depends on the inflow of that matter. So it's much more localized, and so it doesn't have any memory of the previous jet in some sense. So I think that is how we explain these multiple things. But what is interesting is that they seem to be all nested within each other. So I think that may be much more difficult to explain. Like, it can't be completely random. Something is keeping things going in a certain way. So that is still a mystery for us. We don't know. The accretion disk, looking at the disk itself. So this one is, I think this is it's probably an E0 galaxy, and even the other one that we saw was an S0. So we don't have very great, I don't think we have information about the disk. Or even if we do have, we do believe that the accretion disks may not be correlated with that larger, yeah.
This was a great talk. Thank you. Fascinating talk. I have a comment and a question. A comment is, Pratik and Chris Reynolds and I wrote a paper in 2013 suggesting that the changes in direction, a mechanism for changes, because you see this happening in clusters.
Yes, okay.
So that's a really nice sort of connection across the mass scales now.
Right.
My question is that you have this radio quiet AGNs that now are, you've shown that they have jets in them. If I was to put these AGNs on this continuum with the radio loud cluster scale AGNs, what is the parameter? If you could sort of boil it down to one parameter or maybe two, what is the parameter that's changing?
That's an excellent question first. I mean, that's an excellent question. And so we think black hole mass must play a role. That is one thing. The accretion rates themselves, I think they span a large range, which were both in the radio quiet and the radio loud. So there is that overlap. But I'm not sure what else could be. It's something related to the central engine. But I don't know. It's all new to us. So I was just telling somebody else about how these sources kind of, if you're aware of the Mojave sample of AGN, these are 100-odd radio loud AGN which have been monitored by VLBI for several decades now. And these two sources that we found superluminal motion seem to kind of fit in where the rest of the sources are, the radio loud AGN are. So it's interesting. So we're trying to see how to explain all this.
I'd love to talk to you some more.
Yeah, sure. Thank you.
Thank you for a very nice talk. I have a question regarding your Doppler boosting.
I can't
here.
see.
So about Doppler boosting. So that same thing, do you think this is also applicable to a galactic scale? Like we have a few protostellar objects and nearby galactic sources. So we have both kind of things like monopolar jet, and sometimes blue shifted part is missing and sometimes red shifted part is also missing. So do you think it is applicable to galactic sources, or is there any internal mechanism which is triggering this monopolar thing?
Okay, I didn't completely follow your question, but I think it was protostellar jets, and you said sometimes you don't see the jet counterjet. Is that what you were saying?
Yeah. So in protostellar case, sometimes we see that blue shifted part is missing, and sometimes red shifted part is missing.
Right. So I think a lot of the radio quiet AGN free absorption, for example, has been suggested to explain the non-detection of the counterjets. So many times in the very low luminosity AGN, when you don't see one-sided jet, it's attributed to absorption by some kind of intervening medium. Maybe that's the same thing happening in protostellar jets. I'm not sure. But these sources, we are suggesting that they could be because of Doppler boosting effect. So you are not seeing it not because it's not there. It's just our detection, our sensitivity is not good enough to pick up the counterjet emission. But yeah, I don't know if I really answered your question, but
thank you. We'll discuss more.
Yes.
Yeah, Preeti, here. My question is more related to magnetic field. So as you know that these jets majority are controlled by magnetic field apart from, if at all, GR effect,
Yes.
spin effect.
Yes.
So, and radio quiet, radio loud, and field might be playing some role.
Yes.
Is there any kind of direct evidence you find during a survey? Maybe certain critical field is there,
Right.
which is distinguishing.
Right. Yeah. So that's an excellent question. So I think the next step that we have to do, which we want to do, is actually look at VLBI polarization, which is what is done for radio loud AGN. But this is much more difficult because these are radio quiet already. They're very faint, and any kind of polarized emission will be even fainter. So it's going to be a challenge. On larger scales, not on these scales, but larger scales, we have looked at polarization images and found that they have a certain kind of morphology in the B fields. So most of the Seyfert galaxies that we looked at, this is Shilpa's work, and also Binny Sebastian had done some work, that seem to be poloidal B fields on those scales, but we don't know what's happening close to the black hole. So those kind of, there's the Blanford's Nyack, Blanford-Bain, all those things need information on smaller scales, which we don't have right now. But magnetofields are, I think that is what we want to look at as well. Yeah. Yeah.
So Preeti here. So I have one question going back to radio loud, radio quiet. So you said these jets, because of the interactions, they are slowed down. So has there been any attempt, for example, to measure what's the jet momentum in radio loud versus radio quiet? For example, is there a difference in accretion rate? And so thereby discriminating between these two classes of sources in that way.
Right. So momentum, right? Yeah. So I think that is exactly the next stage for this kind of work, is to start looking at multi-phase emission. So what we have is just the radio synchrotron plasma, and we're kind of inferring all this from these very broad kind of correlations that we're observing. But that's the next step, to actually find outflow rates, to find momentum of these outflows. I mean, so yeah, we are not there yet. Yeah, once we have that, it'll be easier to answer these questions. Yes.
All right, so let's thank Preeti once again. We move on to the last talk in this session, Ms. Sim Kanekar.
Hello, is there anybody in there? Ouch. Yes, thank you. Yes. Anything should work. HDMI, I think it's the other side. Thanks. Yeah, I definitely want the pointer. This is a brighter pointer. It should be fine. Yeah, I think this one has the. Okay, so sharing. Yeah, just I can't see actually. Thank you. I see. Okay. Go to the presentation. Yes, sure. Okay. I can't see this darn pointer. Yeah, it's okay. I think I'll stay with this. Okay, sorry for the break. I'm going to be telling you about using 21 centimeter emission studies to probe atomic hydrogen in high redshift galaxies. And this work has been done by a bunch of the folk, listed over, ouch, that was a bit scary, listed over here. But at least certainly my thinking on this subject has been hugely influenced by conversations with the three people over here, the three super PhD students in NCRE, Apurva Bera, Aditya Chaudhary, and Balpreet Kaur, and who have actually done the bulk of the heavy lifting on these projects. So the stuff I'm going to be telling you about is really their work. I've been sitting around the place and chatting, basically. And of course, the background is the GMRT, the telescope that we've used to actually carry out these observations. Before I start, let me apologize. I'm planning to follow Max Delbruck's advice to Alfred Hershey. So the apologies to people who already know a lot about galaxies and galaxy evolution. Can you actually, am I buzzing? Okay, fine. Which is that I intend to assume you know nothing. I also intend to assume that you can learn everything about galaxy evolution in the space of 45 minutes. We'll just cheat 45 minutes, right? Okay, so if you want to understand galaxies, you need to understand a whole bunch of processes. One thing that we've learned, and Arif, I think, referred to this, is that if you want to understand galaxies, we've learned this in the last 20 years or so, you can't just look at the galaxy. You need to look at the circumgalactic medium. You need to look at the interactions between the galaxy and its environment and its neighbors. And so the broad physical process by which a galaxy evolves is essentially, I need to be careful. I've got frozen shoulders. So if I wince when I wave my left hand, it's not because I don't agree with myself, it's because my arm is hurting. So gas basically flows from the intergalactic medium via the circumgalactic medium into a galaxy, and that's ionized gas. And this gas flows into the outskirts of, say, a big disk galaxy, and then condenses out into the outskirts of the galaxy and forms atomic hydrogen. And that's at a temperature of about 10,000 Kelvin. This atomic hydrogen then flows towards the center of the galaxy. It cools. It cools via the radiation from the metals in the disk of the galaxy and forms cold atomic hydrogen. Temperature is about 100 Kelvin or thereabouts. And this gas, the atomic hydrogen, which is in the cold phase, then converts into molecular hydrogen, usually on grains, on dust grains, in the centers of galaxies, and you form the molecular phase. The molecular clouds, the dense molecular clouds, not the diffuse clouds, then collapse under their own gravity and form stars. Yay, we got a galaxy. At which point, the big stars live very short lives, and at some point soon they go boom. And once they go boom, good things happen. They chuck metals into the galaxy, and that increases cooling. Because of the cooling, you form more cold gas, you form more stars, star formation rate goes up. Conversely, these massive stars can also drive outflows. You can have starbursts which drive outflows, and that can drive gas out of a galaxy. And that can actually quench star formation. So the very process of massive star formation can both increase star formation and kill it. It's complicated. So you can actually quench star formation by these outflows of gas, but interesting things happen. The gas that is blown out can actually fall back ballistically onto the disk of the galaxy and can drain back down in the galaxy. It can bring back gas from the circumgalactic medium onto the galaxy and kick star formation off again. So a galaxy's life is fairly complicated, much more than ours. How do we probe all of these things? So the four broad components of a galaxy are the ionized gas, and which is the bulk of this is in the circumgalactic medium, the stars, the neutral atomic gas, and the molecular gas. And the stars, we have a whole bunch of ways of looking at them. The ultraviolet, the H-alpha line, near IR, mid IR, far IR, photometry, the radio continuum. All of these give you information about the star formation rate in galaxies, the stellar mass of galaxies, and even the star formation history of the galaxy. Was it quiescent? Was it bursty? You can get all of this by photometry, for example, across multiple wavebands. For the molecular gas mass, and the molecular mass, let me emphasize, is the proximate fuel for star formation. It's the stuff that actually goes immediately into stars. The only probe that we have which is good is CO emission line, rotational lines in the millimeter wavebands. And for the H1 mass, the atomic gas mass, which is the primary fuel for star formation in the disks of galaxies, the only probe that we have today is the 21 centimeter line, the hyperfine line in atomic hydrogen. So those are the tracers that we have to probe the properties of galaxies. And because you have this whole bunch of complex processes going on, something that I do want to emphasize is that if you want to understand galaxy evolution, you need to understand timescales. If there is one process which takes a much longer time than the other processes, then the evolution of the galaxy will be driven by that timescale or by that process. So you need to actually do a comparison between the timescales of different processes to work out which of these processes is dominant at a given point of time in the galaxy's life. And let me emphasize, these could be different at different times in the evolution of the universe. So that's a question we'd like to address and which I'll talk about a bit towards the end of this talk. So over the last 25, 30 years or so, we've learned a heck of a lot about stars. I mean, our understanding of stars has dramatically improved, of star formation in the universe, has dramatically improved since the time when I was a grad student, 30 years ago. It's a bit scary now. And the reason this happened It started off somewhere in the mid-90s with this, the advent of these spectacular optical and IR telescopes. Keck and the VLT came online, the HST had just come online, and soon after that, Spitzer and Herschel came online, besides the other 8-meter-class telescopes. And that was one nice thing. But the other two things that happened, which kind of tells you that it's not enough to just have good instruments, you actually need ideas. So two things happened. One was that there was a change in strategy, in the approach that people were taking towards understanding galaxy evolution. And then there was a change in the techniques. The strategy was that people realized that they needed to get multi-wavelength information from a large number of wavebands. Because of the complexity of the processes involved, you want to observe the same part of the sky with lots of probes. And so this became the concept of what are called the deep fields, which were basically deep imaging and spectroscopy. It started with the optical and near-infrared, and then moved out into the radio, the X-ray, and so on. And so this shows an example of a whole bunch of deep fields that we have today, ranging from the ultra-deep fields, this tiny region about a few arc-minutes squared over here, all the way to Cosmos, which is the 2-square-degree region over here. The backdrop is a simulation, which kind of gives you, the kind of structure that you see in the universe at redshifts of 2. And that scale over here is a degree. The second thing that happened, and which unfortunately kind of made us radio astronomers much less important for astronomy, was that the Lyman break technique came up in the mid-90s. Until then, people who were looking for high redshift galaxies used radio. The ultra-steep spectrum technique was what people used. And then, sadly, Chuck Steidel and co. came up with this idiotic technique, and suddenly the world changed. Until then, we had a few tens of galaxies at redshifts of about 3 or so. And today, because of Lyman break and the extension to the Gunn-Peterson break, we now have thousands, many thousands of galaxies out of redshifts of 6, and hundreds of redshifts above 8. So the whole universe has changed in terms of our view of it now, in the last 25 years or so. So what has all of this brought us? Yeah, we've got a ton of galaxies. What have we learned about the universe? So if I had to pick one plot to show this to you, I would show this plot over here, which is the star formation rate density of the universe as a function of redshift. So the star formation rate density is like the star formation activity in the universe. And what you see is that there's this rise. These are all measurements, and the black lines are to guide your eye. They are not a fit. So what you see is that there's a rise in the star formation activity in the universe from redshifts about 8 to redshifts about 3. Let me emphasize this is a log plot. It's a log scale. So this is about a factor of 10 higher in star formation activity than here. So the star formation activity kind of rises from redshifts of 8 to 3, and this kind of makes sense. There's not that many stars that are formed earlier, because of which there's not too many metals in galaxies, because of which there's not too much of cooling, so there's not that much of star formation. As you build more star formation, you produce more metals, you produce more cooling, you produce more stars. Fine. At least in a hand-waving way, we understand what's going on over here, at least. This part is a little more puzzling. Here is where it looks as though the star formation activity in the universe basically plateaued for a period of about 3 billion years. Right? And this epoch is often called the epoch of cosmic noon, for no good reason, except that astronomers can't come up with good titles. And we don't quite understand what's going on over here. And that's one of the open questions in the field of galaxy evolution today. And then, from a redshift of about 1 to a redshift of 0 to today, over the last 8 billion years, the star formation activity in the universe has just plummeted. It's dropped by a factor of 10 in the last 8 billion years. So we live in extremely quiet times today, right now. And a big question in galaxy evolution is, why on earth did this thing happen? And if you want to understand, as I said, if you want to understand star formation, you can't just look at the stars. You have to look at the fuel for star formation. And that's what we'd like to do in this talk. So, cutting to the chase, this is a plot of a beautiful galaxy. It's called the Fireworks Galaxy, NGC 6946, in the local universe. And that's a lovely spiral galaxy, just really pretty, right? It's called the Fireworks Galaxy. It's had about 100 supernovae in the last century. Beautiful galaxy. And that's an image by Renzo Boomsma using Westerbork of the same galaxy in atomic hydrogen on the same scale. And what should jump out at you is that, yeah, you see the spiral arms and so on over here, which you also see over here. This galaxy looks very different from this one. It's the same object, of course. But the H1 is much more extended, by a factor of at least 3 in this galaxy, and by a factor of 8 or so in smaller galaxies. So this really kind of tells you that to understand galaxies, it's not enough to just look at the stars. You really need to look at the gas, and that's kind of self-evident. And this, of course, is an image of the galaxy in atomic hydrogen using the 21 centimeter line as a tracer. And that's what people have been doing for the last 70 or so years. They've been using 21 centimeter redshifts of 0 to get all kinds of information about galaxies. So for example, we know the H1 mass of a large number of galaxies. We know the H1 size of galaxies. We know how fast H1 is consumed in the process of star formation via the depletion timescale. We know the distribution of the masses of galaxies in the universe, the H1 mass function. We know how the H1 of galaxies, the H1 masses depend on galaxy type and morphology. We know scaling relations between the H1 mass and the stellar mass, the H1 mass and the blue magnitude, all kinds of stuff. We know how H1 properties of galaxies depend on the environment. There's much less H1 for the same stellar mass in clusters of galaxies than in the field. And we know the Tully-Fisher relations, which connect H1 kinematics to the dark matter properties. So we have all kinds of information about galaxies in the local universe from the 21 centimeter line. That's wonderful, great stuff. We'd like to extend this to higher redshift. If you want to understand galaxy evolution, you need to push to redshifts of 1 or 2 at least. So what do we know about H1 and galaxies, the redshifts above? Let's say 0.5 or so. And the answer is, unfortunately, zilch. Until 4 years ago, 3.5 years ago, we knew literally nothing, except for constraints, about the H1 content of galaxies at redshifts above about 0.5. And the reason is that, although we all love the 21 centimeter line, it's a terrifyingly weak line. It's a hyperfine line. It's a pain to detect this line, right? So the highest redshift at which we had a detection of 21 centimeter emission, I'm embarrassed to say, was 0.376. And we have galaxies today, from JWST and HST, redshifts above 12. It's, embarrassing. So how do you get around this problem? And that's the issue. The one way of doing it, if you have lots and lots of money, is to build a huge telescope. And that's the reason for building the square kilometer array, which we hope will come online, at least in my lifetime. The other way of doing it is to do these ultra deep, crazy deep, much, much more than 1,000-hour integrations, where you look at a field and just spend a lot of time. And of course, there you need to worry about systematic effects, whether noise goes down sensibly and so on. And the problem with both of these, even the SK is not a complete panacea. You will actually only detect the brightest galaxies. And what you want to do is to detect the bulk of the galaxies. And that's not obvious that you will do this even with the SK unless you do super deep integrations with the SK. And so the third approach for normal humans who don't have access to lots of money is 21 centimeter stacking. And that's the approach that we chose to take, to try to understand the properties of the population of galaxies as opposed to individual galaxies, because that is really what you want. You want the population. I don't give a crap about a single galaxy at a redshift of 1.3. Let me thump my chest a little bit, or a redshift of 2. But it doesn't tell me what's going on in the population of galaxies. It doesn't tell me about galaxy evolution. So what exactly is stacking? So the idea in stacking is that your friendly neighborhood optical astronomer gives you a bunch of galaxy redshifts and positions of galaxies in some region of the sky, right? You know their positions, you know their redshifts, and that's a prerequisite for stacking. The positions and redshifts have to be good enough that you can align the 21 centimeter lines from these galaxies. If you can't do that, you're sunk. So that's the game, basically. You need to have good redshifts and positions. Positions are easy, redshifts are hard. And then what you do is that you take your telescope, your radio interferometer, the GMRT in this case, point to that region of the sky, go as deep as you can, as the time allocation committee allows you to do, and then make a spectral cube. Now, the signals from all of these galaxies will be at different spatial locations of this cube and at different frequencies in the cube. And what you do is that you simply cut out subcubes, small cubes, around each galaxy, shift those cubes to the rest frame of each galaxy, align them in velocity and space, and average. And what that gives you is the average H1 mass of that population of galaxies. And what's being done over here is exactly this, but in order to not show it to you in 3D, that's a 2D projection in space, and that's a projection, that's a spectral line cut through the center of the cube. And what you see over here is that you started off with noise. The red circles here are, this is a simulation by Aditya, and you see that the detection basically builds up as you keep adding more and more galaxies, and you can see the spectral line also building up. In this case, we chose that we would see the line once we had about 400 galaxies or so. So that's the game, basically. What you need is a high sensitivity radio interferometer so that you can actually make an image of a region of the sky and separate the galaxies out spatially. You need to have lots of galaxies in the telescope field of view. The more the merrier, because your signal-to-noise ratio goes like the square root of the number of galaxies. You need to have a large bandwidth and large field of view. That's a corollary to this, because the bigger your bandwidth, the more redshift range you cover. The bigger the field of view, the more galaxies you cover. You need to have good positions and redshifts. Somebody has to give these to you. And of course, you need to have redshift such that the 21 centimeter line is inside your observing band. That's obviously a requirement. You need to be able to observe the line to see it. And people have tried this. Jairam and his students, and then Shiv, Dwarka, and I tried this with the GMRT for a period of 15 years or so. And we all, I'm happy to say, failed miserably. We didn't see a damn thing. We got upper limits on the H1 mass, which is boring, quite honestly. I spent my life on upper limits. It's not really fun. So they were all 2.5, 3 sigma detections. You kind of say, yeah, you know, if I squiggle my eyes, I can see a bump. Not fun. And the reason for this was actually simple. The reason was just that the old GMRT had a bandwidth of only 33 megahertz, 32 in the original GMRT, 33 with the software backend, and narrowband receivers. What that meant was that in a single observation, you could only cover a tiny range of frequencies, which meant a tiny range of redshifts, which means a small number of galaxies. And this made life hard. So things changed in 2018 when the upgrade of the GMRT was finally completed, and suddenly we got access to, one, wideband receivers, where you had these, you could cover a large frequency range with the receiver, but equally important, a new correlator. And the correlator gave us a bandwidth of 400 megahertz. And this suddenly meant that we could cover a huge fraction of if you like, of the receiver coverage in one shot. In the case of lower frequencies, you cover the entire receiver coverage in one shot. For the highest frequency, most of the receiver coverage. And even nicer was that the sensitivity of these receivers was very similar. So that's a plot of the sensitivity in units of G by T-sys times 1,000, ignore the numbers, as a function of frequency for the 3 highest bands of the GMRT. And you can kind of see that the sensitivity is roughly flat for most of this region, except for the holes in between, of course. And that's the staff-mission rate density plot. So we started a bunch of projects with the upgraded GMRT. The first was a 350-hour band 5 survey of the extended Groth strip, which covered this frequency range. It actually covered 1,000 to 1,400 megahertz, but this is the range in which we had redshifts. And so that covers the declining part of the evolution of the staff-mission rate density. Then we did a 510-hour band 4 survey of the 7 deep 2 fields at a ratio of 0.74 to 1.45. That was using this receiver, covering about 560 to about 820 megahertz. Hello. Thank you. And that covered this interesting redshift range, which included both the decline in the staff-mission activity in the universe and the flat part over here. And this is where we thought we would see action. We're also doing a follow-up now of 130 hours or so on the Cosmos field at the same redshift range. And then we pushed to even higher redshifts using the band 3 receivers, and we're covering this frequency range, which corresponds to this redshift range, about a redshift of 1.8 to 3.3 in the Cosmos field. And I'm going to be talking today a little bit about the 350-hour survey that Apurva Bera did for his PhD, and mostly about the 510-hour band 4 survey. I'll tell you why I'm going to focus on this part of the redshift range, the frequency range. So jumping straight on, so we did the 350-hour pointing on the Groth strip. We chose the Groth strip for the same reason that I mentioned earlier. It had redshifts in our redshift range of interest. I had a redshift of roughly out to 0.4, had good redshifts. And so, but the thing was that, we chose to simply go and observe one pointing. The Groth strip is this long strip over here, and the thing over here, the white things are the deep 2 redshifts, so the deep 2 galaxy survey. The green band over here are redshifts in the deep 3 galaxy survey. But the 3 things that you see in cyan, magenta, and red, the 3 boxes over here, are HST imaging. So you can see that the HST imaging is sitting right over here and doesn't cover the extended regions. So we chose to simply focus on this tiny region because we have much more information about galaxies in that region. And of course, the second reason we chose this was that we're at sufficiently low redshifts that we have a chance to actually get individual detections. So if you go and hammer away at this redshift range, you should be able to see a bunch of individual 21 centimeter emitters out of redshift of 0.4, which would have been super exciting. And so that's what Apurva did for his PhD. And what was disconcerting for us was that we actually got very few 21 centimeter detections. And this was really surprising. We only have about half a dozen 21 centimeter clear detections, about 6 detections, and a few which we're not confident of. And this is puzzling. And curiously, private communication with Jacqueline Van Gorkom, the JVLA has been doing a similar survey, the Chile survey, led by Jacqueline and her group. And they too are seeing far fewer detections than they expected. So it is possible, I wouldn't stake my my right arm on this, but maybe my left, given that it's in bad shape right now, it's possible that there's evolution happening even at redshifts of 0.4 and down. And so that's something to worry about. But what we did was that, so this shows the galaxies that we had in our pointing with redshifts. The backdrop image is the GMRT continuum image of this field. This is currently the deepest GMRT continuum image ever made. It's got a noise of about 2 microjansky per beam. And that's a stacked 21 centimeter emission line from all of these galaxies. So it's detected about 8.5 sigma significance. And now you can play all kinds of games with that detection, which I will not tell you about. And the reason I won't tell you about these games, is that, unfortunately, the field of view of the GMRT at these frequencies is quite small. And the redshift range is quite small, which means that we cover only a small cosmic volume in this single pointing. And that's bad news, because it means that we are limited effectively by cosmic variance. So although the results are interesting, and I can tell you about them offline or later if you like, I would still be wary about trusting them too much at this stage, just because the field of view is small. Maybe we got unlucky, and that's a region in the sky where there are not that many gas-rich galaxies. We don't know. And so, as I said, Chiles is actually doing a similar-sized region in Cosmos, and they are surprisingly seeing similar results to us. And we are waiting for the mighty H1 results, which will now give us a third field. All three of us are going to be hit by cosmic variance, mighty H1 the least of all. And that's just because the volume that you cover at these redshifts is just small. Mighty H1 has the best of the three. So moving on to higher redshifts, and this is now the GMRT cold H1 at redshifts of 1 survey, the CATS1 survey. And here we were using again the Deep 2 Galaxy survey, and there are these 3 fields of the Deep 2 Galaxy survey with 7 separate pointings we chose for the GMRT. And what you see remarkably is that this is the GMRT beam. The red circle over here is the GMRT beam at 650 megahertz, and you can see it's a remarkable match to the Keck coverage of the Deep 2 Galaxy survey. So we've covered this entire region in 7 pointings. The redshift accuracy is great. It's about 60 kilometers per second. And as I said, we're covering this interesting region in terms of redshift evolution, going from about redshift of 0.74 to a redshift of 1.45. So cutting straight to the chase, we stacked the emission for about 11,500 galaxies, and this is what we saw. So this was a spectacular detection. This is about 7.5 sigma over here. The original one was about 4.6 sigma, and then adding more, we went down to 7.5 sigma. And that's the spectral line that you see by taking a cut through the stacked cube. So detected loud and clear. We now have a detection of 21 centimeter emission at an average redshift of 1. The first take home is that the average H1 mass of these galaxies is about 1.4 times 10 to the 10 solar masses at a redshift of 1. The average stellar mass is about 10 to the 10 solar masses. So the first take home is that if you compare this average H1 mass to the average H1 mass of galaxies in the local universe with the same stellar mass distribution, same average stellar mass, these galaxies have about 3.5 times more H1 than today's galaxies. So the first take home is that there's much more H1 in galaxies at a redshift of 1 than there is today. Okay, interesting. Not entirely surprising, perhaps, but interesting. What else can you do? You can ask the question that, yeah, there's a lot of H1 in these galaxies. How fast is it eaten up in the process of star formation? So the way you do this is that you can measure the star formation rates of these galaxies, the average star formation, the median star formation rates of these galaxies, by stacking the radio continuum. So we did that, and you can simply take the ratio of the H1 mass to the star formation rate, and that gives you the H1 depletion time, or the H1 consumption time, the time scale on which you eat up the H1. And that tells you how much time the galaxy can continue to form stars at this rate without the addition of new H1 via accretion or minor mergers or what have you. And we know these numbers for the local universe. That's the H1 depletion time scale. The blue points are for galaxies of the XCAS sample in the local universe from Barbara Cartinella and collaborators. And these are, again, stellar mass matched. The red points are for the GMRT CATS1 survey as a function of stellar mass. The first thing you'll take away is that the depletion timescales are much shorter at redshifts of 1 than at redshifts of 0. The gas, although there's lots of gas, it's eaten up much faster at redshifts of 1 than at redshifts of 0. But the really scary thing is this point out here. At the highest stellar masses, more than 10 to the 10 solar masses, the gas is eaten up at timescales of less than a gigayear. And that is astonishing. That's comparable to the timescale in which molecular gas is eaten up, which is the line that you see over here. That doesn't change much with redshift. So take home is that in the most massive galaxies, although they have lots of H1, you eat up the H1 really fast because the star formation rate is so high. Now, this is interesting because the gas depletion time is a gigayear, and I said that we're covering the redshift range 0.7 to 1.5 gigayears. And that corresponds to a time period of about 2 gigayears. So if the gas depletion time is indeed a gigayear, I would expect to see evolution within this redshift range, from a redshift of 1.4 to a redshift of 0.7. And so what we did was that we broke up the sample into 2 redshift bins. Redshifts of 0.74 to 1.25 and 1.25 to 1.45, again did stellar mass matching, and that's the stacked spectrum. The orange one is for the higher redshift bin, the blue one is the lower redshift bin, and even visually you can see there's much more 21 centimeter signal in the higher redshift galaxies. And let me emphasize, these galaxies have the same stellar masses, same stellar mass distribution exactly. And that's what you see over here in terms of the H1 mass. The H1 mass drops by a factor of 3 from a redshift of an average redshift of 1.3 to an average redshift of 1.0. So on a timescale of a gigayear, the average H1 mass of galaxies with the same stellar mass distribution drops by a factor of 3. That's really sharp. And so what we think is happening is that, and remember, this redshift of 1 is exactly when the star formation rate density starts to drop. So what we think is happening is that the decline in the star formation rate density from redshifts of 1 to redshifts of 0 happens because the H1 in galaxies is consumed very rapidly by the process of star formation in the most massive galaxies, and there is not enough accretion from the CGM or from minor mergers to build up the H1 reservoir of galaxies. Okay, sounds interesting. Where do we go from there? What we can also ask is, where are the baryons in galaxies? We know in the local universe, let's say in the Milky Way, the baryons in the Milky Way, the baryon composition of the Milky Way is dominated by stars. Most of the baryons are in stars in the Milky Way, about 90% of them. And so if you take the X-gas sample, for example, about 65% of the baryons are in stars, 33% are in atomic gas, and about a few percent in molecular gas. You can play the same game now, because now we have measurements of the atomic gas at these 2 redshifts. And what you see is that the amount of mass in stars drops by about a factor of 2 to 30% by redshifts of 1. The amount of mass in molecules goes up to about 15%, but the amount of mass in atoms, atomic hydrogen, goes up to about 40%. But things change even more at redshifts of 1.3. And about 70% of the baryonic mass of galaxies is in atomic gas at a redshift of 1.3. Atomic gas basically dominates the baryonic mass of galaxies at redshifts above 1. And that's something which we did not know prior to this work. Moving on, I also said we have information with scaling relations from direct observations in the local universe. We can do the same thing at high redshifts. So this is now a plot of the H1 mass as a function of stellar mass. The 3 red points over here from the Deep 2 survey, again binning by stellar mass. Same thing for H1 mass versus absolute B-band magnitude. 3 points over here are from the Deep 2 survey, again binned in magnitude. And the orange curve or line over here is from the local universe. The blue line over here is from the local universe. So the first thing you see is that the H1 mass-stellar mass relation goes up as you go to high redshift. And curiously, there's not much evidence for evolution in the MH1-MB relation. This is the tightest correlation that we have in the local universe for the H1 mass with optical properties. And certainly within 2 sigma, the green and the blue curves are consistent with each other. And we would really like to understand what's going on over here. I personally do not find scaling relations terrifyingly exciting or interesting. They're kind of blah. But the more interesting thing is, what can you do with scaling relations? And it turns out you can do fun stuff with them. So Sandhya Rao and Frank Briggs, about 30 years ago, realized that you could use the MH1-MB relation, which is what people had gotten in the early 90s. You could combine that with the B-band luminosity function to actually determine the H1 mass function. This was in the days before the wide field H1 21 centimeter surveys like high pass and alpha-alpha and so on. And these gave the first estimates of the H1 mass function. And one thing that they missed was that another factor that you need to put in is a scatter in the MH1-MB relation. And this, ouch. And this was realized by Apurbo in a paper a year and a half ago. So we did this at a redshift of 1. And this plot shows the number of galaxies above a given H1 mass as a function of H1 mass. The blue curve over here is from alpha-alpha by Jones et al. And the green curve over here is from the CATS1 survey. And what you see is that there's more than 10 times more galaxies with an H1 mass more than 5 times 10 to the 10 at redshifts of 1 than at redshifts of 0. So there's lots of galaxies with a huge H1 mass at a redshift of 1, and which is, again, a huge surprise. This has implications for individual searches for H1 emission from galaxies. Okay, so I'm going to jump straight on, I'm going to pass straight through this. I'm just going to show you one more result, which comes from the MH1 M star scaling relation, where we can actually use the different scaling relations, MH1 M star, MH2 M star, and star formation rate M star at different redshifts to actually probe the evolution of the baryonic mass in galaxies. And so this is a plot of now the baryonic mass. You're actually tracking the evolution of baryons in individual galaxies. I can tell you how to do it later if you like. But what this is telling you is the baryonic mass in a galaxy at a redshift of 1.3 divided by the baryonic mass in the same galaxy at a redshift of 0. And what you see remarkably is that for the most massive galaxies, so 1 basically implies that all the baryons in a galaxy were already in place at a redshift of 1.3. And after that, you're shuffling them around. And what you see is that for high mass galaxies, high stellar mass galaxies, all the baryons were already in place. You're actually losing mass over the last 9 billion years. Even for the Milky Way, about 90% of its baryons were actually in place at a redshift of 1.3. And all the way down to about 2 times 10 to the 10, 70% of the baryons were in place by a redshift of 1.3. So I'm going to cut straight to my conclusions over here. I told you about 4 large GMRT surveys, and the punchlines are listed over here. I think, Arif kind of showed a thing of the H1 mass function. And I should say that, we are now at the point where we can, for the first time, actually measure the H1 mass function at cosmological distances, at a redshift of 1. The only simulation that we can see that matches us right now, matches, is perhaps a strong statement, that is consistent in a hand-waving way is SIMBA right now at a redshift of 1. All the others are way below what we're measuring. So I'll leave you with that. Thank you.
Thank you, Nissim. Questions?
Excellent talk, Nissim. So the upshot of the talk is that most of the baryons which have been accreting through the IGM into the galaxies have been sort of somehow from redshift of 1.5 till now have been sort of trapped in the CGM or pushed out. Is that?
So I would say it's even more than that. Remember, this is the thing that you're seeing over here is gas in the disk. So this is, so yeah, it is, I mean, they may have gone back and forth, but this is actually the gas was already in the disk of the Milky Way, for example, at a redshift 1.3. And it's cycling in the disk of the Milky Way. Yeah. So it's not, I mean, there is obviously back and forth with the CGM, but this is actually stuff in the disk. Yeah, there's not that much stuff coming in.
Hi, Nissim.
Yeah. Hey.
Yeah. So my question is about this fall-off that you showed in the H1 masses as you go from, a very short redshift range, right?
Yeah.
So do you know, when you do this stacking, you need redshifts. And typically, the redshift success rates can start to change as a function of redshift, whether you have elliptical galaxies or more red and dead galaxies compared to star-forming galaxies.
Sure.
And have you seen any differences in these redshift success rates as a function of type within that redshift range?
Yeah, no. So the Deep 2 survey is nice in this regard. That's one reason we chose the Deep 2 fields, because they've basically done a magnitude-limited redshift measurement, and they look at the O2 lines for all galaxies with R of with R brighter than 24.1. And it turns out that this picks out blue galaxies.
Yeah.
You're basically picking out galaxies that, at redshifts of 1. It's picking out galaxies which are blue because they are basically rest frame 3000 angstrom selected.
Right. Yeah.
Right? So you're picking out bluer galaxies. In fact, 90% of the Deep 2 galaxies are actually blue galaxies. We've excluded all the red galaxies in our sample. We are only working, this is star-forming galaxies. All of the results here are for blue star-forming galaxies.
Just for star-forming
Yes,
galaxies.
and blue star-forming galaxies.
Okay.
So they've been color selected.
Okay. And the second question was related to the scatter in the MB, the scaling relation that you talked about.
Yeah.
So for this scatter, is there a way to constrain it?
Yes.
Or, and how do you go about it?
Yeah. So it turns out that you can actually, you need the scatter. And the way we've gotten this is by assuming that the scatter does not change from redshifts of 0 to redshifts of 1, which you might say is a strong assumption, right?
Yeah.
It turns out you can actually measure the scatter. And we intend to do it. The way you can measure the scatter is that for a log-normal distribution, the ratio of the median stack to the mean stack gives you the scatter. Mm-hmm. So we can actually do that. We already done it for the redshift, for Apurbo's work at a redshift of 0.3. We could measure the scatter, but with somewhat large error bars. It turned out to be consistent with the scatter in the local universe. We can't measure the scatter right now. We can barely measure it at a redshift of 1, but we will be able to measure it with the 580R integration that we're doing right now with Deep2.
So how big is it, like in terms of deck?
Sorry? So in the local universe, it's about 0.26 decks.
0.26.
And we don't, at a ratio of 0.3, it's less than 0.3 decks, less than 0.35 decks.
So there was okay, quickly, brilliant talk, Nissim, and brilliant piece of work. So can we go to the slide where we were showing the the average baryon mass in stars from redshift 0 and redshift 1.3, some very final, that one. No, I think with the one with stellar mass, the one that with stellar mass, from redshift 0 and redshift 1.3.
Okay, the baryon, you mean
later. That one, yes, that one. So you said that these are similar kind of galaxies.
They're main sequence galaxies, star-forming main sequence galaxies.
And you have measurements, so are they also identical in stellar mass? I mean, no, when you say that they're similar mass.
They have a range. I'm not saying they have similar mass. I'm saying that in this particular work, what we have done is that we have taken scaling relations.
Yes.
Scaling relations give you the dependence of various properties on the stellar mass, right? And so we have now the scaling relation over a range of stellar masses.
Yes.
So in this, for example, for 21 centimeter, we have the scaling relation from 10 to the 9 solar masses up to 10 to the 11 solar masses. For H2, we have a scaling relation from about 5 times 10 to the 9 to about 10 to the 11. For star formation rate main sequence, we have about 5 times 10 to the 8 to about 10 to the 11. So once you have the scaling relation, given a stellar mass, I can tell you what the star formation rate is, I can tell you what the H1 mass is, and so on. So now I can actually track, and that's something that unfortunately, because of my nasty collaborator here, I wasn't able to tell you about, but you can basically track a galaxy as it evolves along the main sequence by looking at how the gas goes from atomic gas to molecular gas to stars.
Oh, so when you say that these are similar galaxies at these two redshifts, that is mean by the similar kind of star formation?
They're all main sequence galaxies.
They're all main sequence galaxies.
But this curve, remember, is looking at the evolution of one galaxy. You're actually looking at how a galaxy evolves, and you're doing that for all the galaxies from a stellar mass from 10 to the 9 solar masses up to a stellar mass of 10 to the 11 solar masses. You're asking the question, how do each of these galaxies separately evolve?
Nissim, hi. Here.
Where?
Here.
Great, thank you. I'm losing my eyesight.
All right. So you have a nice stacked spectrum. I understand that there will be orientation and other factors. But have you looked at the width of the spectra? And can anybody, anything can be commented on the dynamical mass or the dark matter content of the average galaxies?
Yeah, that's a good question. So there's two things we can do. One is that we can try to get the H1 mass halo mass relation, and we've actually been doing that. With the 510 hours, it's tricky. Sensitivity is not quite there. The other thing you can do, which I think is even cuter, is that you can get the Tully-Fisher, the stacked Tully-Fisher relation. And it turns out, so we did this for a single bin in magnitude. It turns out, remarkably, the velocity width that you get for in the 21 centimeter, stacked 21 centimeter, is exactly what you expect within, well within the 1 sigma error bars for the average B magnitude of these galaxies. So the evidence is that, and we haven't written that up as yet, the evidence is that the Tully-Fisher relation does not evolve from redshifts of 1 to 0. We have binned the thing in two absolute magnitude bins to actually measure the Tully-Fisher relation. Remember, this is just taking a single point and saying, does it sit on top of the Tully-Fisher relation? It does. Now what you'd like to do is try to break it up into bins and then separately measure the velocity, the full width Raff maxima of the two stacks. We've done that as well. It turns out that the errors now, because we started off with about a 7.5 sigma result, now when you do both of these, you get to about a 5 sigma result, 5.2, 5.3 sigma result, and you get, you get the full width Raff maximum. But the constraints that you get at the Tully-Fisher relation are not sufficiently good, at least in my opinion. So certainly the next run that we're doing right now, which is 580 hours on Deep2, should let us nail this question. We should be able to actually measure the Tully-Fisher relation from the stack.
Thank you.
Last question.
Hi, Nissim. Excellent. Is it possible to use this Salpeter mass function and then start with some initial mass of neutral hydrogen and then evolve it to the star formation and then see what is observed with the observation? Does it really match with that?
So, okay, so this is actually doing effectively that, but not with the mass function. We are actually taking galaxies, we are taking the observed properties of galaxies, which is main sequence evolution, and asking the question, how do these galaxies evolve? Assuming that they evolve on the main sequence. That's the only assumption that has gone in. If they stay on the main sequence, then we know the scaling relations between the various H1 mass, H2 mass, stuff formation rate, and so on. So we can tell you how a galaxy evolves. The thing of taking a theoretical mass function is that you will actually have to go through the whole complex physics. That is a much harder challenge. I mean, they are limited. I mean, that's what numerical simulators try to do, and that's what Arif was talking about. That's a harder thing to do today.
All right, so let's thank Nissim and all the speakers of the session. We break for tea now and be back at 11:40.